About radiation, which is very important problem in radiation in pencil code. Then I will tell about boundary conditions and using so-called buffer zones. And finally I will show the last results, which was obtained actually in this early but anyway, so it is something already. And then we mention about non-resolved so about just a bit about the general idea of this project. So the general idea is to try to describe as much as possible accurately the physics on the surface of a neutron star to explain the so-called quasi-theoretical oscillations. So first of all, I can say that now there are many models, but actually all models are also based on the speculations, some estimations, and there is no accurate numerical simulations now. And so we tried to go further and to describe it numerically. So about the history. So the topic started in 1977, so the first paper was by Green in 1977. So they proposed a model of 1D boundary layer. So the picture is quite simple. So the disk comes to the surface of the star, and at some radius, the gas starts to fill the presence of the star, and so in a very narrow range, the Keplerian profile, velocity profile is destroyed, so the gas is slowing down, and it happens in very narrow region. And on the other hand, so the thickness of the disk increases, and so the estimations show that the size of this region is determined by this expression. So it is determined by sound speed, Keplerian velocity, and the size of the neutron star, and the size of the disk, this size, is also determined by these three parameters. So that was the first model, and now it's named as classical boundary layer. So next model was proposed by Nagama Sinyarov in 1999. So they tried to describe the behavior of the gas on the surface, and so-called the model is a spreading layer. So again, gas comes to the surface of the disk and then spreading over the surface. And so what they did, they constructed the 1D model, started from this point somewhere near the equatorial plane, set here some bit strange boundary conditions, but all what we can do, and they also describe one-dimensional structure by analytical equations, and then some results. Get some results. So the huge advantage of this model, and this is the model of the boundary layer, the model of the spreading layer, is that they are analytical models. And so it means that it's very easy to repeat the result and get the same, repeat the calculations and get the same result. But on the other hand, so it's clear that all physics, very important physics, happens near this equatorial point. And of course physics in the spreading layer and boundary layer will depend on this point. But here it's already 1D approach is not valid. And this is at least 2D picture, maybe 3D, but at least 2D. And what we want to do, so we want to describe this area, so the area near the equatorial plane. So now about the formulation of our numerical problem. So again we have this star spreading the gas over the surface, and we consider this region. So I'm sorry that I show the disk not in this position, but for you probably it's easier to understand, because then I will show you some pictures in the pencil cord, and so the Z coordinate will correspond to this right direction. But anyway, so this is this is the rotational axis. Anyway, so the rotational axis of the star. So about our problem, numerical problem. So of course we make some simplifications. So first simplification is that the size of this region is much smaller than the size of the star. So it means that we replace the spherical coordinate by the Cartesian coordinate. Then we assume that all derivatives in rotational direction are zero, and then comes to the 2D description. And now what we have? We have the calculation area, Z direction, as I told you. So Z direction coincides with the regular direction, X direction is along the surface of the star, and Y direction along the rotational axis, parallel to the rotational axis. So as I told you, the size of this layer is much smaller than the size of the star. So it means that in this region, so the gas is slowing down, and the velocity, rotational velocity, decreases from say 10 to 10 down to 0. It happens in a very small region, so it means that huge kinetic energy is converted to the thermal energy. So it means that in this region, so the temperature, gas temperature is quite large, and it's about 10 to 7 Kelvin. So it means that the radiation pressure is quite important here, and it can be comparable or even larger than the gas pressure. And of course it should be included in the code. And so what I did at the beginning, so I included the radiation pressure in momentum equation, and losses due to radiation in the energy equation. So we consider optical peak case, at least now. So now let's discuss a bit the boundary conditions. And let's start from the 1D equation. So the first step was of course not 2D but 1D approximation. So let's forget about X direction and stay with Z direction. And let's see the boundary conditions we set. So first boundary is in the disk zone, and the second boundary is near the star surface or the star surface. So the huge problem in this topic, in this physics scenario, is that boundary conditions, boundary conditions are determined by actually physics inside the calculation region. So it's very important to understand. So everybody knows that solution depends on the boundary conditions. But in our case, so boundary conditions depend on the solution. So what I mean? So let's consider disk zone. So we know that in principle, so it's disk, and rotational velocity should be close to the Keplerian. But it cannot be exactly the Keplerian one, because in that case there is no accretion, so no spreading, and no problem. And it means that there should be some deviation from the Keplerian velocity. But so this deviation depends actually on the physics here. It depends on the ability of the star to let gas go inward. And so it means that the boundary conditions, at least for the rotational velocity, depends on what happens here. And the same story on the surface of the star. So let's imagine that we have a metal sphere with a temperature of about 10 to 7, and the gas which comes to the sphere is spreading on the surface. In that case, so everything is clear because so we just set the value 10 to 7 and then see what happens with the gas. But in our case, actually the gas forms the surface of the star. And so the temperature of the star actually depends on the, say, temperature of the gas and kinematics of the gas as well. So that's the reason why we decided to use the buffer zone, so-called buffer zones. What does I mean? So I will explain further. But I would like to mention about also the third zone, which is mass-sink zone. So why we use this zone? So we wanted to get, at the beginning we wanted to get the stationary solution. And to get the stationary solution, it's necessary to remove the same amount of gas which comes from the upper boundary. That's why we use this mass-sink zone. So now let's discuss property of every zone. So this zone. So only in this zone. So I added some specific terms. So let's start from the rotational velocity. So there is such a term which means that the rotational velocity approaches the Keplerian one. But due to this coefficient or due to this term, so there's some freedom. So it means that this boundary value adjusts to the physics aside with calculation region, adjusts to the solution. So the same story with the radial velocity, that component of velocity. So that velocity approaches some value which is determined by the parameter of the problem, so-called accretion flux, which is proportional to the density multiplied by velocity, and divided by rho. And about temperature, so again, so there is some freedom. It's not exact value. So temperature of the gas in this region should be close to this value, but it can be different. So again, there is some freedom. About star zone, so it's more or less clear. So y and z velocity approaches 0, and so this term looks a bit complicated, but it's very simple. So the numerator is 0, then the temperature is constant. So it means that so we want to get the constant temperature in this zone, which is close to the parameter of the problem. Yeah, and the last about the matching zone, so it's also very clear. So this is the sink term, which just means that so we remove the same amount of mass which comes through the upper boundary. So it's characterized by this parameter, which is flux. Now let's discuss two-dimensional problem. Again, there are three zones: star zone, this zone, and a sort of mass-sink zone. So now it's not necessary. So there is a so-called surface zone. And let's start from the disk zone. So in 2D, the situation is already a bit complicated comparing with 1D, because here we cannot use the crystal flux as a parameter. And the reason is that we don't know in what part of this zone there is accretion and in what part there is excretion of the gas. And so instead of accretion flux, we use the density profile. And So this term, that means that density approaches to this distribution of density always along the, of course it's x here, along the x direction. And this distribution is determined by the hydrostatic equilibrium in the disk. And so with this x component of velocity is more or less clear, so we assume that the disk is in hydrostatic equilibrium, so there is no vertical motion in the disk. And so this is also clear, so rotational velocity approaches the level one. And so with this component, so the situation is a bit complicated, but not so huge. So this term means that the next layer is just to the previous one. And actually I cannot explain you exactly so why it works, but it works, and that's the evidence. So really, I just can say that. So due to this term, the physics in this so z component of velocity adjusts to the physics inside the region rather than physics so in different parts of the disk.
Yeah, but it tries to establish a zero gradient, right? A zero radial.
Yeah, it means that, yeah.
Gradient.
Yes. But so the interesting fact that so if there is no such term, so it doesn't work. That's some additional limitations, some additional conditions which just helps, I don't know, to helps to get some right physics, something like that.
And all the z dependents are x dependents throughout this page, right? It's all x dependents actually, right?
Here?
Yes. They're also in the last equation. Everywhere, right? Psi, or is it psi of z?
No.
It's psi of z, yeah?
This one?
I thought you corrected yourself at one point and said this should have been psi of x, no? No, but it's psi of z, I see that, yes. Okay, then I must have been confused.
So,
yeah.
You are talking about this?
Yeah, I thought.
Of course it's z.
It's z, that's right.
Because we have this direction.
Yes.
So these functions just mean that no more that just that for these terms, so they exist only in the corresponding zone, not more. And of course it's z. But this is x because it's the vertical direction in the disk. Here should be. So roll disk should be in this direction. Yeah, star zone. So here is the same story. So velocity vector approaches 0 and temperature approaches star temperature. And about the surface zone again, so the same story. So any attempts to set some boundary conditions, so symmetric boundary condition, anti-symmetric boundary condition, something, concrete values, so just lead to crash of the code. And I use the same approach just for all parameters. I include the terms which means that the next layer is just the previous one. And again it goes. And again, I can say in principle, in that case maybe it's not so clear. So we know that the gas should come from this boundary, then comes to the surface and turns and come out from this surface zone. So it means that all what happens here should depend on the gas upstream. And so due to these terms, we just say that, okay, so let's say that all physics here depends on physics here, all physics here depends on physics here, and so on and so on. actually the result. Good, okay. So, first of all, it works and the code doesn't crash. But now, so what we have? We have that, so this size is smaller than the thickness of the disk. If we assume the hydrostatic equilibrium, so the disk, the thickness of the disk should be something like this, 2 times larger. But the problem is that the size of the boundary layer, spreader layer, is extremely small. But on the other hand, all physics happens along this axis. And it means that here we should have quite many points to resolve the structure and to get something reasonable. But, so this size, physically this size, if we want to get all the disks, is much larger than the size of the boundary layer. It means that here should be at least the same amount of points as if we have twice of the length, so it means that we need more points here. And it just so one needs to add points, and it takes quite much time. So that's why at this moment I stop here, and I want to see that. So indeed I can get the stationary solution, but now it's not a stationary solution, it's calculated, it's in the process, but it doesn't crash, it's okay already. And so the last, what I want to mention about the problem, the nearest question which should be discussed and included. So now there is no radiation viscosity. So to compare with other modules, with the Nagamov-Siniak module, for example, it's necessary to include the radiation viscosity. Now it's only some molecular turbulent viscosity, it's just a constant number. What does it mean? It means that, so because the radiation is huge and it's anisotropic, so the most radiation comes from the surface of the star. And so due to radiation, so photons go upwards, but the gas goes below the surface, and so the radiation just accelerates the gas, and this is some sort of viscosity. So it should be included, should be something called the tensor, because of antisymmetry, and it's for the future.
Isn't there thermal diffusion in the boat?
Diffusion?
Yeah.
Thermal diffusion, yeah.
Thermal diffusion.
But that's your heat, that's your radiation, of course.
Yes, of course.
Doesn't it work on the same way, or is it
This is the
something completely different?
This is the radiation diffusion, but but this is losses due to radiation, not more. So, but this is diffusion approximation because we consider optically thick phase. But again, so there should be some term with viscosity, and probably it should depend on some gradients, velocity gradients or something. Actually, nothing new, but I haven't done it.
I mean, so what it really is, of course, is if you have a shear layer, for example, then across the shear layer you can have an exchange of photons. One photon goes from the stream over there into the lower one, and another photon from down here to up. And of course that couples these two layers and causes simply viscosity. And so in the momentum equation you should have a term which has to do with the local shear. Very different. Right? And simply the coefficient has to do with the radiation field.
Yeah.
But is it then? But it's an anisotropic fusion.
Yeah, that's what you have.
Okay.
Yeah. So actually, that's all what I want to tell you. So that's
Okay.
thank
Yeah,
you.
thank you. Very good. Yeah. So we see here that using buffer zones was really very much the clue to everything, right? And you said something at one point about enforcing hydrostatic equilibrium. Can you show us this equation again? I mean, one would expect to see some terms like the gravity in that expression.
Yes, so of course the gravity is included, and now there is two components, so gravity, one is radial component, now it's x, but I don't have that equation. So.
But I mean, how is this being enforced, the hydrostatic equilibrium? So just by turning off everything else, perhaps, yeah?
No, so that's just the additional term which looks like, so d over d, something like here, and here is dm over, say, z, x over z, something like this. Here should be some.
Oh, okay, right, yes, indeed.
Not more. And so it's, this term is everywhere in the calculation zone, but it's a bit, so it's not so good because if we have a spherical surface,
yes,
so it's okay only in this part,
yes.
But here that's not good. But on the other hand, so this side, at least at this moment, is quite small, so this error is not so huge. On the other hand, so then we use Cartesian coordinates. That means that we say that the surface of the star is here rather than here.
Yes.
And so this, maybe this is not so bad because again we have some buffer zone, which gives them some sort of freedom anyway. But
yes.
So this term is included.
Yes. Now, but in the continuity equation, in the density equation, shouldn't one there have a term which has to do with the stratification? Because stratification leads to a density gradient.
In the zone, yes.
And so therefore you would expect a term like this.
Yeah, this is. So
exactly
this term.
Yes. Okay, and this exactly, yes.
Zone. And this is the exponential.
Exactly. Yeah. Now I understand. Yes. Yes. So I'm saying this because Fourier said similar things. He could maybe use a similar trick. So look at this. The rho disk of Z, or which is really rho disk of X, yes, is actually the target stratification, which is hydrostatic. And so with this zone, she's basically enforcing this hydrostatic stratification asymptotically near the boundary in a soft way.
But have you tried using the freezing that we have in the code?
So let's just get a special solution with 2D.
Yeah, because what I see there, the equations which are showing, they look pretty much like what the freezing does. So as
what
long
is
as freezing.
Freezing?
Yeah.
So he's keeping the values fixed at boundary.
Yeah, exactly, yeah.
But I mean, that is a more extreme way. This is a softer way of doing this.
True, yeah.
So, for example, Toby had reported about a similar problem just a few days ago, where he was using the frozen thing, and then he got these strong gradients on the boundary, and then instead of freezing, he was using also buffer zones now.
Sure.
And it sort of helped him.
But in the freezing, you can also add buffer zones by width, right? I mean, you can have drastic freezing, which is step function, right? But if you add width, you have something softer too. So we would reproduce this.
But that
in the global disk, in the global disk, I also use buffer zones.
Do you mean the size, because it's just size, a heavy side function for you, whereas size is something smooth here, or what?
Yeah, but I mean, the question is, you're talking about in time, of course. You make it soft in time. Okay. You make it soft in space.
Yeah.
And
so you
make it both soft in time and space, but in particular, of course, in time, so that in other words, you could have something which is frozen, but not immediately, only after a few time steps, only after 5 time steps, it would be very close to almost frozen. But if the first time step, it wouldn't.
Yeah, what I'm saying is that how are you doing those buffer zones in the code? I mean, are you making several different sub-routines for each buffer zone?
No,
Or,
no, I just...
or is it a general
So
thing?
that's very simple. So if we have in the code some, say, value, yes, something like that. Yes, here is A1 or A2, yes, and so. Yeah, and what I did, I just say, so for some values of n, which is say n smaller than nx, yes, and here's nx minus n, like this, yeah, I include this term. So this term exists only for these values of n, and that's all. It's exactly in the equation.
This stuff isn't all checked in at the moment, is it? Is it all
Now I'm in the process of removing all my stuff in the special module, and I already did it, but I didn't make check-ins. So
what I was going to say, I mean, I assume you've got to do something clever because you've got a term that depends on dt, which must be a bit of a pain. At the first time step, you don't know dt, right?
Yeah, but so it means that at the first time, so there's no this term, but it's just the first step.
You just don't do it on the first sub-step.
Yes, no. Yes, no.
Ah.
Oh, yes. No, this term at the first step, but it doesn't matter actually. So this term just...
Oh, that's brilliant. Yeah, sorry, I could have thought you don't need to do
this
it.
term just a bit, how to say...
It's a bit less than it should be. It's about, well, worse, it's a third of...
To change the physics in the direction what I need. So just show, but so just no, I don't know. Say I want the Keplerian velocity. I want some value which is close to the Keplerian velocity, and I put this term and show the code that I want this term, this value. Say this value.
Yeah, Jeff Anders,
But
I'm
it's very
about to ask
small.
something that I want to answer from you in a second, so join us a second, if you're not. But so you've got to understand this term. You're not calculating it in the first sub-time step. So my first question is, are we allowed to do that? Because then you're not solving the same equation at each sub-time step. Can you do that in the numerics of a Runge-Kutta multi-step scheme? Can you solve one equation at one sub-time step and still really have a Runge-Kutta scheme? Is one question.
But it doesn't matter if it's not exactly Runge-Kutta.
It's just one step.
Yes.
Yeah, but I mean, all of the stability analysis and everything, and the theory behind Runge-Kutta, does it work if you solve a different?
Yeah, but it's just the beginning of a long simulation. I mean, you have 100,000 steps or something in your simulation.
You see, I know
It's the beginning of every time.
I don't think that is a big problem.
So you say
Is this only done at the beginning of your simulation?
it's on the beginning.
You don't have to have the buffer zone for the rest of the simulation.
No, it's
No,
the
no,
opposite
no.
thing.
It's all time.
All time except on the first time step.
The first sub-time step, right?
No, the first time step.
The first
First
is
time
all
step.
time
First
step.
time step.
Yes.
First time step. But you see, so my initial condition.
No, sorry, my problem is that you've got a dt on the right-hand side. Now, dt isn't calculated in any time step. dt isn't known until the end of the first sub-time step.
Oh, that's what I mean.
It's the dt from the last time.
Ah, right, okay. So you use
And that means that there's only one dt behind.
Right, okay. That also solves.
I'm sure it's not the merger of stable,
That,
but it's such a tiny offset. Right?
yeah, okay. That's
Did you see what the problem? What the question was? The question was simply, what was the value of dt? And I think it's a irritation actually. I mean, one should 5 times delta t is not really supposed to have anything to do with the time step. It's just a tau value. It's a time, something with a unit time, which would be approximately, roughly, I mean, not much short, certainly not shorter than a few times delta t. So you could, for example, take 20 times delta t, but then you may be worried. So 5 is approximately the right value. And so I think you should actually replace this by a tau. By say, for example,
you do a moving average of dt instead of just...
But it doesn't matter. No, I think it's rather better to have it to have that one constant independent of delta t. So if delta t all of a sudden does become very short, this one should not become very short. It should be
But you
kept
would just take
fixed.
the delta t as the form, I mean, just as the delta x divided by the sound speed or something. I mean, some kind of constant. That doesn't depend
Yes.
on the, I guess it's also some.
So you just use some other time scale. Yeah.
Yeah, but I mean, you can just take the subsonic time step, for example, which is just the sound rate, right? Just like delta x divided by sound speed, which is different.
That's a good possibility, yeah. The advantage then is that you're fixing automatically any possible time step constraints on that one would be identical to the time step constraint for the sound speed.
Yeah.
And so this would not, of course, affect the time step.
Oh yeah, that's very good.
And now it's subsonic.
Yeah. Cool.
But I think you should just make it an input parameter, and it should have the dimension of time, and you will adjust it, and then you can, in the paper, you can say delta t is this and this many milliseconds or something. It will be simply something with milliseconds.
I maybe not so understand what you mean, because that's a technical problem, nothing with physics. That's just some
Yeah, right.
way to get the solution.
Sure, but you want
and
to-
so if you just put just some boundary conditions. So I tried it in 1D. So even in 1D it doesn't work. So if you put the boundary conditions, so you immediately get some wiggles, because so you immediately get some inconsistency. And I explained why it is so, because boundary conditions depend on the solution. That's the problem. Then so we use such a way, so it means that technically we a bit so we give some freedom for the boundary condition, that not more. And so this value is just some I don't know, some calculation experience. So I put here 5, I put here 20, and then 1, and just see so how it's. If I see that so the code tries to make this velocity close to Keplerian faster than other parameters approach the necessary parameters. So it means that so this step is too small. It's necessary to increase that, nothing more.
What is the form of this function? What's that letter name?
Psi.
Yeah, exactly.
This is just unity here and 0 here. And the same with this function. So it just means that so this function exists. So these terms, the corresponding terms exist only in the corresponding terms.
So it can totally look like the freezing thing which we have in the code. So that's why I am not understanding quite well why you need to code everything once again if it's a feature that we have it.
But then can you explain me if here's a time scale. So in your freezing, is there a time scale?
No, it's in space.
Right, and therefore that means in her case that would mean that instead of having 5 times delta t, she would have 0 times delta t.
No. It's just that he does, of course, have a time step. It's just that 5 delta t is 1.
No, what? 0.
No, it's not. It's not divided by 0. It's the same term.
It would be divided by
It's
0.
bottom.
No, it would be divided by 0. Of course.
I'm not understanding why.
Here, can you show the equation again?
So the difference between this term and that term is 5 dt equals 1.
I mean, all you're saying is on the boundary. I mean, first of all, this one is 1 on the boundary, right? Yes. So if this one, if you make this one smaller and smaller and smaller, all the other terms become very unimportant, because this whole thing becomes very, very big. So now make it equal to very, very small, 0.
Right, yeah.
Then you can basically say this is all 0, so this one is equal to that. And that means this one is frozen to this. With zero adjustment time.
What I'm saying
Instantaneous,
is,
that is.
yeah.
Okay, that's one possibility. Now, that's extreme. And she is saying that causes figures. Instead of avoiding these figures, she is putting some buffer, a temporal buffer. There's also what Toby has been doing, which was the solution to one of his problems.
Well, this is why I thought what Vlad was doing was the same, because
Yeah.
Vlad wrote his right-hand side turn down on the board.
Yeah,
And it was precisely that.
What I am saying here
The
is
term that Toby went away and implemented was the term that Vlad wrote down,
Yeah.
which was this.
we can actually have a subroutine in which we will have a term which will be that one here, right?
Mhm.
And then we can make this one here and then this one here as passing parameters to the subroutine. And then, wow. And then with this thing, it will be general, right? Because here, you see that these two things here, they're the only things that actually change in this term. So then I'm using that thing there in the global disk and Dolbe too, right?
Yeah, but the question is there any temporal adjustment possible? So
Temporal adjustment. Well, the temporal thing here will be that term, right? Will be this term here, which in my case doesn't have anything to.
if you wanted to do that, I think then you should say
with the temporal thing, but
yes.
here.
Then you should say so you at the new time and t should be equal to. In your case, if I understand you correctly, you're saying this is equal to u and t equal to 0, right?
Yes.
Some u not at 0.
Yeah.
Okay. Now, if you want to make it soft, you want to allow some excuse if you can't immediately do this. Setting this to abruptly completely different value may be too extreme for the code and may create biglets. So therefore, one can say that one takes maybe only 1/5 of this plus 4/5 the previous time. So u of t minus delta t. See what I mean?
What is the UT thing?
That gives you the possibility of saying so it's like saying I'm asking you to pay me back all your money. I mean, you borrowed some money, right? For example, and
No, but
then
so you're talking about the
saying
difference
you pay me back 100 kroner right now. So there's no time to wait until lunch, for example. You have to pay it right now. So I come to you, you have to pay me now. So if I say I give you a temporal buffer, then I say, okay, it's enough if you just pay me 10 krona right now. And you pay me the 90 kronas over the course of the day.
Of course. No, but the difference between what you're talking about and what Vlad's done is that you have a term on the right-hand side of the differential equation, right? So if you so he doesn't set u equals, he sets the rate of change of u is such that it tends towards the value. What's
Okay,
the
then maybe
difference between this?
okay, then can you write down exactly what it is?
Well, I was trying to say, the term that Vlad wrote down yesterday is that. It's just that dt equals 1.
Is what?
Or dt equals some fixed number. So Natalia,
But is what? Is that you mean?
so Natalia has it so that the damping time varies with time. So the damping time in your code is a function of time.
But that's just
and it evolves. Whereas
No.
the damping time in his is fixed. Tau. There you go. He's done it.
So
That's what he's got.
what I'm saying here is that we can make it here like a subroutine in which we will pass this term here and then that.
Okay.
Yeah, like
But in her case, it's also fixed. That's what I said. So if the time step becomes shorter, or should have been fixed at least.
It should have been fixed.
Yeah.
In which case you do want exactly what he's got. So this is the point. The only difference between what you have and what Vlad has is that tau is a function of t in Natalia's case. Full stop.
So I just said that I also try to use this approach that you
Okay, now how do you determine R? So it's called freeze, yeah? And R of... I mean, of course...
I see why I was going with when I said I wanted to ask these two, because I was going to say, do we need some general method in the code for having
I mean, I understand.
right-hand dependency, but it's really done already, so...
I mean, that's of course what you are doing in the other part of the disk, right? Yeah, of course.
the inner two.
Yeah. And the inner two. Yeah, exactly, of course. I mean, that's all the same. But we normally call it buffer zone.
I don't call it a buffer zone. I am calling it a freezing region, but it's the same thing.
Yeah, I mean, but anyway, we always call it buffer zone. We have been using this in all kinds of simulations, and
yeah, there's loads of. I mean, before you actually start working on the code, there were buffer zones in various variables, right? And
but
there was a temperature.
So another question is, but for you have a specific profile, right?
That's what it is, right?
You have a specific profile for your buffer zone.
Yeah, I do.
So she cannot use the same profile. So she
No,
doesn't.
but I can make it general, and that's no problem. But the freezing.
But how do you make it general?
It is quite general there in the freezing thing. Apart from the functional. Yeah, the functional on the freezing